Let's say we're designing a simple aluminum block 1 inch long, half an inch wide, and a 1/4 inch thick. Now, my machinist is very good, but she can't make perfect parts, so we have to give her some allowance. We need to define the allowable variation for each dimension. We'll use length and width tolerances of ±15 thousandths of an inch, which are reasonable for a machined aluminum block of this size. We'll use a stock tolerance for the thickness, which will be adequate for the intended application. Calling out a stock tolerance necessitates the need for a properly defined material specification, which we should do anyway. We'll use ASTM B209 and select 6061T6. In this case, stock tolerance is ±12 thousandths. The part is also going to need a clearance chamfer and a counterbore hole. This type of hole is typically used for a socket head cap screw. Which means that this surface is likely an interface. Ideally, we would prefer the axis of the hole be perpendicular to this interface surface. We'll position the hole from the chamfered corner using regular linear dimensions, each with a tolerance of ±5 thousandths. The item is now completely defined, so let's see what this all means. For the length, width, and thickness, we can show the limits of acceptability as a set of inner and outer boundaries. All parts that fall within these boundaries are acceptable, while any items that do not fit within the boundaries are considered non-conforming to drawing specifications. We received the part from the machinist. In this case, the actual part we received has a bit of a taper on a few of the sides, but are still within tolerance. In this part, with length, width, and thickness within print tolerances, let's understand the shape of the tolerance zone for the hole based on the current dimensioning scheme. In this case, we defined a 1/4 inch nominal dimension with a ±5 thousandths tolerance from the long side, establishing an implied relationship between the hole and the edge. Since the only reference for this 1/4 inch dimension is with the long edge, this surface becomes our reference for subsequent measurements. To visualize this tolerance zone, we set the long edge of the part on an inspection plate to establish the reference plane. Then we create two parallel planes, centered a 1/4 inch above the surface plate, and spaced 10 thousandths apart. The axis of the actual hole, relative to the long edge, must fall between these two planes. We perform a similar inspection for the short edge as well, establish the reference plane, create two parallel planes, centered a 1/2 inch above the surface plate, and spaced 10 thousandths apart. Note how the planes remain parallel to the associated reference surface. For the part to be good, the axis of the actual hole must simultaneously fall between both sets of parallel planes. Having a limit dimensioning scheme to position the hole causes the final shape of the tolerance zone to be completely determined by the shape of each reference surface. In this case, the hole was machined perfectly orthogonal to the interface surface and located exactly a 1/4 inch and a 1/2 inch from the long and short edges respectively. Almost a perfect part, however, the axis of the hole falls outside the tolerance zone due to the taper of the reference surfaces. An otherwise good part would be rejected as non-conforming because of the method used to dimension the drawing. A significant drawback to this type of dimensioning scheme is the inability to define the interface surface as a reference. For this item, the relative orientation of the hole, compared to the long and short edges, is of no concern. It is only the distance from those edges that is important for the hole. Functional tolerancing provides an alternative approach to traditional limit dimensioning, allowing for any feature to be defined as the primary reference surface. Subsequent references can then be assigned, in order of priority. In this manner, the final shape of the tolerance zone remains constant without deference to the actual shape of the reference surfaces. When used to position a hole, the tolerance zone will typically be a cylinder, orthogonal to the primary reference.